So I think I'm the one introducing Marica. Yeah, Marica is a postdoc here, the Newsborn Institute, Marie Curie Fellow that started a few, well, yeah, 6 months ago, more or less, a bit less than this perhaps. And today she's going to talk about this work that we finished recently, which, well, she's going to talk about point functions and hyperboloidal slices, Black Hole Perturbation Theory. Please go ahead.
Okay, so thank you for the nice introduction. So as Rodrigo mentioned, today I'm going to talk about essentially our joint paper that you can find at this link. So this is, and maybe some also some new findings that came out of discussions with Lyon and London more recently. And essentially, I'm going to talk about, I'm going to provide a space-time interpretation to the Confluent Heun equation in Black Hole Perturbation Theory. So the first thing, oops, let me see why it's not moving forward. Okay, so the first thing I'm going to do is to very briefly introduce what is Black Hole Perturbation Theory. Then I'm going to provide a definition for the Confluent Heun equation. We mainly analyze two forms of the Confluent Heun equation, what is called the general form and the non-symmetrical canonical form. Then I will move on discussing the Teukolsky master equation for the Kerr family of spacetime. In particular, this talk is about the radial Teukolsky equation and how to recast the radial Teukolsky equation as a confluent Heun equation. And in relation to this, we introduce the concept of Heun slice. Then in the remaining part of the talk, I will revert back to the radial Teukolsky equation written in Boyle-Lindquist, move to compactified hyperboloidal coordinates, and essentially work within the minimal gauge. So we choose for these two ways of fixing the gauge, the so-called radial fixing gauge, Cauchy fixing gauge. And then we will, what we did is to analyze the resulting equation and to figure out if this is a confluent Heun equation or not, and eventually using tools that have been developed for confluent Heun equation to investigate a little bit the behavior of the solution to the resulting equation. And in the end, of course, there are the conclusions. So why perturbation theory? So the study of black hole perturbation has a long history, as we all know, with the work of Regge Wheeler, then Zerilli, Vishevara Press, and many more. But the main question is why we do want to study black hole perturbation. First of all, one example can be the stability analysis. So to study what happens to a black hole when we perturb this black hole with very small disturbances. The black hole ring down. So what happens to a black hole after a merger of two black holes when the black hole settles down by emitting gravitational waves. So we can study the gravitational waves and then analyzing, understand a little bit more of this of the ring down phase. And then, of course, to perform gravitational wave astronomy, to then understand the signal which are detected by LIGO, Virgo, and so on. And in the future, of course, LISA. But there are many more other applications of why one will look at perturbations of black holes. Now, since we are mainly interested in Kerr, the main question one has is how we can we perturb the Kerr space-time? So if one thinks about just perturbation of the metric, one can think of linearizing the Elstad-Fried equation around the Kerr metric and try to derive a set of perturbation equation. If you try to do this, what you discover is that you have some perturbation equation, but they don't fully decouple. And so the way of separating the equation becomes quite a challenging task. So maybe perturbation, to perturb the metric is not the way to go. And in fact, Teukolsky in his seminal work, what he did is instead of looking at metric perturbation, what he did is to use the Newman-Penrose formalism and derive perturbation equation for the so-called Weyl scalar psi0 and psi4. And in the end, derive is celebrated Teukolsky master equation, where here I just wrote the sourceless master equation, where T is just the Teukolsky, the general Teukolsky operator, let's say. Now, the beauty of this equation is that it decouples, and in particular, by using, for example, the Fourier decomposition into frequency domain, we can decouple this equation into a radial and angular equation that can be solved independently. And this is now the point where they gave rise to this main reason why this work and talk exist. It is because the radial equation can be written, in fact, as a confluent Heun equation. Now, the question is, what is a confluent Heun equation? So first of all, I have to say that there is a very long, there's an increase of interest for this equation within the black hole, the black hole perturbation theory and gravitational waves community, because of this very fact that the radial Teukolsky equation can be written as a confluent Heun equation. But what is a Heun equation, first of all? A Heun equation is a second-order linear differential equation with 4 regular singular points. We have the general points y0, y1, and y2, and we have the point at infinity. So we have 4 regular singular points. Now, when 2 of these points coincide, let's say y1 and y2 coincide, and infinity becomes an irregular singular point, this is when you have a confluent Heun equation. So in the end, a confluent Heun equation is a differential equation, the result of a Heun equation with 2 regular singular points and 1 irregular singular point. Now, as I mentioned when I was discussing during the introduction, we have many forms in which this confluent Heun equation can appear. One of these is the so-called general form. Here I'm just taking the definition coming from Rimbaud, book of Heun differential equations. And it's an equation that looks like this. So AI, CI, E, BI, and D are the coefficients of the equation. YI are the regular singular point of the confluent Heun equation, and then that we label as Y0 and Y1, but they can be arbitrary point within this domain. And then we have the point at infinity, which is the regular singular point. Now, this equation admits 2 linear independent solutions. One that can be derived locally around the regular singular point that can be written in this form. So the which behavior around the singular point is dictated by this exponent rho I. And then we have an asymptotic solution provided by an expansion around infinity, whose behavior is dictated by this new, the new exponent, sigma and eta. Now, the kappa are constant that can be determined by initial boundary conditions. Now, this characteristic exponent, the thing that I would like to stress is they are directly related to the coefficient of the Heun equation, the confluent Heun equation. So once you know the form of the confluent Heun equation, you can obtain explicitly what is the form of this exponent, and then know how your solution behave locally and asymptotically. So this is about the general form, but this is not the only form. Another form that is the one that appears more often when discussing the radial Teukolsky equation as a confluent Heun equation is the so-called non-symmetrical canonical form. The non-symmetrical canonical form arises by taking the 2 regular singular points, y0 and y1, and mapping them into 0 and 1 via a transformation of this form. So it's called non-symmetrical just because the 2 points are mapped into 0 and 1. You have also a symmetrical form where you will have -1 and 1. So you will have some form of symmetry between the singular point. But this is not the only ingredient to obtain this non-symmetrical canonical form. One is to also introduce an homotopic transformation. So an homotopic transformation is just a map between continuous functions. So you can deform a continuous function into another continuous function. So our solution y to the general form of the equation is mapped into a new solution z to the non-symmetrical canonical form via transformation of this form. Essentially, what you do is to deform the solution around the regular singular point 1, the regular singular point that corresponds to z 0 equal to 0, and then the point at infinity. And in this case, to dictate how you're deforming around this point, you have this coefficient mu 0 and mu1, that again, they are related now to the coefficient of the general form of the equation. So given these two ingredients, and then some manipulation of the resulting coefficient of the new equation, you can then obtain this form of the equation, which is the one that you see very often in literature, where this gamma, delta, epsilon, alpha, and q are just the result of some manipulation around the new coefficient of the equation that you obtain after performing this transformation. Now, this equation...
Sorry,
yes.
Can I ask a quick question? In the previous
yes.
slides, you had a square term. If you can go 2 slides back. Oh, this one, yes. So the term that divides BI is a square, and that looked to me like an irregular singular point, but then it goes away and it becomes only, there's no more squares anymore. How did that magic happen?
Yeah, so you mean here?
No, the boxed equation.
Oh, here.
Yes, that term. Because I thought that if it's a square division by square, it's an irregular singular point. Am I wrong?
So this is, so this equation contains also information. So this is the yi, you mean? Okay, so I see it. So this is 3, which is the regular singular point. You're right. So this must be the point y3, I think. Is it?
The third one.
Let me think about it. So this is the general form. So this is yi, which is squared. And then, so this goes from 0 to 1. No, I think this needs to stay like this, because it gives you rho I, which is the regular behavior, the solution.
Okay. And then there's no square terms after you do the transformation in the next slide.
Yeah.
Interesting.
Okay. So Rodrigo wanted to say something.
Yeah, no, I think this is precisely the singular point. So the square would be appearing in the if it is a irregular point, it would be appearing in the first derivative piece. So usually to test if it's a regular, you multiply the term with the derivative.
Yeah, you have it here.
By the thing and take the limit, and you multiply by something squared and take the limit from the piece with the no derivative. So this is still and transforming to the non-symmetric canonical case is precisely final transformation where the BI is 0.
I see.
Yeah,
okay.
Yeah. So when you move to the other one, essentially you're asking that BI and the new D are equal to 0, and this is achieved by introducing this. So the way these are related to the previous coefficient is to get rid of those two terms.
So that takes care of the square term, and that. Okay. Thank you. That makes sense.
Yeah. Okay. So I was at this point. Okay, so we can solve this equation and have, again, 2 linear independent solutions that essentially are of the same form as the one that you will have for the general form, but with new characteristic exponents, because I would have to remind that the characteristic exponents of the local and asymptotic solution are always related to the coefficient of the differential equation. Right? So these two now are the main form that we will that I will mention during this talk. There will be another form that I will discuss when time comes. Okay, so what about now the spacetime that I would like to consider? So what we consider is the Kerr family of spacetime, which is just a 2-parameter family of solution to the vacuumized field equation describing a stationary axisymmetric rotating black hole. The Kerr metric written in Boyer-Lindquist coordinates looks like this, where m is the mass of the black hole, it relates to the angular momentum of the black hole, and in particular, delta r is the function that contains information about the position of the event horizon and of the Cauchy horizon that you can explicitly know as in terms of a and m by looking at when this function is equal to 0. Now, since we are interested in sub-extremal case, then we ask that that A must be strictly less than the mass, the black hole mass. Now, this is our background spacetime, and we would like to consider perturbation of this spacetime. So the perturbation, as I mentioned in the beginning, are dictated by the Teukolsky master equation. So in this Boyer-Lindquist coordinate, the Teukolsky master equation for the master function psi looks like this. And where S describes the type of perturbation. For this talk, I will not fix S unless this is necessary. So we'll try to be as general. I will try to be as general as possible. What we do is then to separate the Teukolsky equation to the frequency domain by introducing a Fourier decomposition. This Fourier decomposition eventually will lead to two equations. One is called the radial equation for the function R, and an angular equation for S. For this talk, we are only interested into the radial Teukolsky equation. The radial Teukolsky equation has this form. Now, if you take this equation and divide from the coefficient of the second derivative with respect to R, which effectively just dividing by delta, you can obtain one form of the confluent Heun equation. So you can rewrite the radial equation as a general confluent Heun equation. Here, I didn't explicitly write down the coefficient. I just wanted to say that the form of the equation is like this, where now the singular point Ri correspond to the regular singular point being the Cauchy horizon and the event horizon, and we have an irregular singular point corresponding to the point at infinity. So as per the way we construct solutions to this type of equation, we know that we have in the asymptotic region, we have a local solution around the horizon that has this form, whose behavior is dictated by this rho HP and rho HF, where this governs the behavior around the future, what we call the future event horizon and the past event horizon. And we have an asymptotic solution that is obtained by an expansion around R for R that goes to infinity, whose behavior is dictated by eta and sigma. Here, I briefly mention what is the form of this, what is the explicit form of this exponent, where with omega c and omega h, we refer to the angular velocity of the horizon, and with this bar x, I think it's called, what we do is to just label what is the surface gravity of the horizon. Now here I've added a Carter-Penrose diagram of the time-like slices obtained that correspond to the Boyer-Lindquist obtained by a foliation obtained by the Boyer-Lindquist coordinate, for the reason that from now on, this solution R I would often refer to as the Boyer-Lindquist solution. What I mean with this is Boyer-Lindquist solution to the radial equation, whose behavior is dictated by the exponent that I've listed here. Okay. Now this is one form of the radial equation as a confluent Heun equation. What we can do, and what is done most of the time, is to take this form of the radial equation and then transform into the non-symmetrical canonical form. Again, here I just put the form that the equation will look like once you do the transformation. The transformation corresponds to a coordinate exchange, so we pass to Z, so then now RC and RH are mapping to 0, 1, and then infinity stays at infinity. And this non-symmetrical canonical form is achieved by introducing a homotopic transformation between the Boyer-Lindquist solution to the new solution. New solution, I mean solution to this equation. The homotopic transformation now is telling us how the Boyer-Lindquist solution is deformed at the horizon, corresponding to Z equal to 1, at the Cauchy horizon, corresponding to Z equal to 0 at infinity. But the interesting feature of this procedure is that now the equation that you obtain doesn't give you a unique choice for mu c, mu h, and nu that determine how you're deforming your solution, but you have two possible choices for each exponent. So this means that in total we have 8 combinations for the triad mu c, mu h, and nu. Okay, so once we re-derived what it was already known in literature, what we did is then to ask, what is the effect of the S homotopic transformation? So what is the formation doing essentially? So what the transformation is doing is to modify the behavior of the Euler-Lindquist solution around the singular point by changing the coefficient of the local and asymptotic solution in this way. So the one that you see underlined in dark red correspond to the former Euler-Lindquist exponent for the solution, and then the tilde ones are the new coefficient that tells us how the solution to this equation behaves locally and asymptotically. Okay. So this is one. The second thing that we ask is, what is the spacetime interpretation on this 8 configuration? So very often we read that it was very much stressed that all these 8 combination leads to suitable confluent or an equation. So the question is this relevant? What it means? What is the meaning in terms of spacetime of these 8 combination? So what we did is then to revert back to the Teukolsky equation, and then what we did is to take the radial Teukolsky equation in Euler-Lindquist and proceed with a coordinate transformation. So we pass from the t and phi Euler-Lindquist to new coordinate t tilde and phi tilde, where h and this is psi just some function of R. But also what we do is also transform the master equation. So what we did essentially taking the Teukolsky equation, transform the master function in this way, where zeta is a new function that will depend on also on the spin coefficient, and then implement the Fourier decomposition for in the frequency domain of this new master function. What we obtain is then we can relate the Euler-Lindquist radial function that you will normally obtain by the standard frequency domain decomposition and by looking at the standard radial equation for Teukolsky, and the new radial function that you obtain by this method. So by introducing this change in the master function and this coordinate transformation. Now, given this form, we thought about comparing this with against the S homotopic transformation that we know relates the Euler-Lindquist solution to the new solution of the non-symmetrical canonical form of the radial Teukolsky equation. And then by this comparison, what we discover is that we can identify HR, psi r, and zeta as modification of the tortoise the tortoise coordinate, the angular, what we call the angular tortoise coordinate, and the delta function that contain information about the position of the horizon. So explicitly, you can write down this function in this form, where the coefficient a0, a infinity, b infinity, and so on are different for all the possible configurations, for all the possible choices of mu c, mu h, and nu, and determine then how the solution behave at infinity and around the horizons. So what we did is then to look at each configuration choice. So we chose mu c, mu h, and nu in all the possible ways, and figure out what is the form of h, xi, and zeta, and chi and zeta, and then plot them. So the plus and minus that you see in this plot correspond to all the possible choices of mu c, mu h, and nu. So plus, plus, minus will correspond to mu c plus, mu h plus, and nu minus. To each of them correspond a choice for h, c, zeta, And so you have a corresponding coordinate transformation, and of course also a different transformation for the master function. Upon looking more closely at the detail of this surface and then also on the look like, but also the geometrical properties, what we discover is that two combinations corresponding to plus, plus, and minus, and mu, and minus, minus, plus, effectively corresponds to just taking a coordinate choice corresponding to outgoing and ingoing null coordinates. So the effect of the S-homotopic transformation with the coordinate choice to Z is the same as taking the radial Teukolsky equation in Borel-Lindquist and passing to outgoing or ingoing null coordinate. But then for the other 6 choices, we have very different behavior that we didn't manage to link to other type of well-known coordinate transformation. But what is interesting is that it seems that all these configurations always come in pairs, and that's why they are represented in the same Cartan-Perros diagram. In particular, they have interesting behavior around infinity. Some of them have interesting behavior around infinity, like these two combination, and some other ones around I plus and I minus. So in the end, the S-homotopic transformation, all with the Z, and this H combination are nothing than just changing the foliation of the spacetime. So working with a different foliation of the spacetime. Okay.
Sorry, can you explain
yes.
why they become time-like and how that happens in the frequency domain?
Yeah, so I think, first of all, I think that because of how I'm plotting this in Mathematica, you can see that this is, I don't think that it actually accumulates in I0, but it really becomes very, I would call very tangential to the horizon. This is due to how I'm choosing how I'm fixing, how I'm choosing the angular momentum effectively. So I've noticed by plotting the surface by changing kappa and moving more towards to the extremality that this type of future where you see that is very, that it seems very, very no is just a feature of the, and just a feature of the resolution of Mathematica when I get close to that point. How they become time-like is due, so if you, so let me just figure out. So we usually do this, so when we study the geometrical properties of this, of these surfaces, what we did is to look at the gravitational perturbation by setting S equal to 2, and then looking at the Kinnersley and the Kinnersley tetrad associated to this foliation. And so when we look at this vector, we can see that the normal vector is the one for a time-like surface. So this is how we investigate more the property of the slice in terms of this. So I don't know if it's a satisfactory answer.
I just got confused a little bit because it looks like the surfaces become time-like and they're not just space. I understand why they become null. I don't quite see how it works that they become time-like. Somehow the H must grow, something like that. But it's okay. You can keep going.
Yeah.
Thank you.
Yeah, I mean, okay. Okay, so we have this now. Out of this discussion, the takeaway message is that instead of, so one can look at the coordinate transformation of this form that will map the Borel-Lindquist solution into this new solution that has the same effect as requiring as introducing an homotopic transformation for the general form of the Confluent Heun equation. With of course also the new coordinate Z. Now, given this, and given that this transformation really really reminds us of a possible hyperboloidal transformation, where we have this. Thus, the radial Teukolsky equation, when we pass to compactified hyperboloidal coordinates, take the form of a Confluent Heun equation. So to try to answer this question, what we did is to take the radial Teukolsky equation written in Boyle-Lindquist, so effectively take this slices and then introduce some hyperboloidal coordinates, and then try to study the equation that we obtain. So this means that what we did is to introduce the hyperboloidal formalism. So we introduce a coordinate transformation of this form, where lambda is just a scale factor, and h is the so-called height function. Then we also introduce a compactification for the radial coordinate of this form. This compactification will map the point corresponding to 0, RC, and RH, so the singularity, the Cauchy horizon, and the event horizon, into new points sigma 0, sigma c, and sigma h. Along with this, the introduction of this coordinate also provides a conformal rescaling of the metric, with a conformal factor equal, the been chosen has been sigma over lambda, where lambda again is just a length scale, whereby the conformal metric is regular in the domain 0, sigma 0, when sigma 0 is whatever point this point is mapped into. So because of this, this requires that the original Teukolsky master function needs to be transformed into a new master function by transformation that will not only involve delta, but also the conformal factor. So then now the relation between the solution, the Boyle-Lindquist solution to the radial function, and the what you can call the conformal radial function looks like this. So where h, as I said, is the height function, and chi bar, c bar is just is what we call the angular tortoise coordinate. Now, so the way we compactify the radial coordinates, so we consider an hyperboloidal foliation within what is called the minimal gauge. So the minimal gauge will mean that the rho that appears in the compactification for R, so when we pass from the former radial coordinate to the new one, is expressed in this form, where rho 0 now the former rho 0 guarantees that the radial function, the radial transformation maps the horizon into the position of the event horizon into sigma h equal to 1. So we can also write an expression for the new position of the Cauchy horizon and the black hole, the new position of the black hole singularity, so that now we can have a whole transformation for which the gauge is entirely fixed by the choice of rho 1. So to introduce the height function, what we do is also introduce the dimensionless tortoise coordinate, which is essentially just the tortoise coordinate divided by length scale, and introduce the contribution to this dimensionless tortoise coordinate in terms of a term which is regular infinity, one which is regular at the horizon, one at the Cauchy, plus one constant term. And then once we do all the calculation, what we figure out is that essentially the height function will always be given by a sum of all these p's, and sometimes you also have a constant term added to it. For the angular tortoise coordinate, one can make a similar consideration, so that the angular tortoise coordinate will look like this. But as I said before, we can fully fix, at this point, we can fully fix the hyperboloidal foliation by fixing rho 1. Now, to fix rho 1, we can make different type of choices. The first choice that we made is to set rho 1 equal to 0. This corresponds to the so-called radial fixing gauge, because then the transformation between R and sigma becomes very simple. This radial compactification in particular map 0 to sigma 0. Sigma 0 in this coordinate is a point at infinity. The label 0, C, H, and infinity just refers to whatever position, whatever point R belong to in this coordinate. So rho 0 is at infinity, rho C is at some finite position, rho H as sigma H is at 1, and sigma infinity now correspond to, is located at 0. Now, what we did is then to study the radial Teukolsky equation written in this coordinate, and it turns out that the radial Teukolsky equation is not a confluent Heun equation. This is essentially because the hyperboloidal transformation within this gauge, what it does is to introduce an additional singular point to the equation. So we have 3 regular singular points, sigma 0, C, and H, where sigma 0 is a point at infinity, and 1 irregular singular point that corresponds to sigma infinity equal to 0. Now, the reason why there is some confusion around this is because there is an alternative form of the confluent equation obtained by just from the non-symmetrical canonical form by doing a transformation similar to this, so whereby your coordinate r is mapped into 1 over sigma, that for which if you look for, if you try to recast your radial Teukolsky equation in that form, it seems that you are able to find all the necessary coefficients. But this is because the form that now the radial equation has sigma 0, which is at infinity, as a regular singular point. So this means that whatever coefficient belongs to this point is not there. So the way one can figure out if this point is actually become an ordinary point of the equation, for which then, so that it is missing from the equation, is to then try to map it into a new function z. And if you do that, what you discover is that now it doesn't it doesn't assume at all a canonical form for the confluent Heun equation, so it doesn't remind us of the confluent Heun equation. And here you can clearly see that the point that used to be at infinity now is mapped to a finite position. And then if you study what type of singular point this is a regular singular point. So in conclusion, you have 3 regular singular points and irregular one. So you have more regular singular point than a confluent Heun equation will have. So at this point, what we did is to investigate, so at this point, what we did is to try to use the tool developed for the confluent Heun equation to study a little bit with more depth the radial equation resulting from this type of so in the radial fixing gauge. So if you compare the relation between the Boyer-Lindquist solution and the solution to the radial equation in this radial gauge fixing for the hyperboloidal foliation, you can rewrite it as an homotopic transformation. So now we're doing the converse. We are taking the coordinate transformation and then look at the relation between the solution and rewrite it as an homotopic in terms of an homotopic transformation. By looking at the coefficient, the exponents, you can see that now we have mu c, mu h, and nu, this bar coefficient that are, if you look at the coefficient that appear for the Heun configuration plus plus, they really look very similar. But novel feature of the radial fixing is that now you have an additional coefficient, mu infinity, which is non-zero, which is something that doesn't happen for any other Heun configuration. And this point correspond to this mu infinity correspond to a deformation around r equal to 0, which is in the end the additional singular point that is introduced in this type of gauge fixing. So via this consideration obtained via an homotopic transformation, one can definitely support the conclusion that the radial Teukolsky equation in compactified hyperboloidal coordinates with the radial fixing gauge is definitely not a Heun equation because we have an additional singular point. Here you can see the behavior of some hyperboloidal slices within this gauge fixing, and then see that these slices cross the horizon, cross the Cauchy horizon, which is at a finite position, and then somehow accumulates around r equal to 0. So this calculation and consideration seem to suggest that then any hyperboloidal, any choice is compatible with an hyperboloidal coordinate choice within the minimal gauge would lead to something that is not a confluent Heun equation. And this is the part in which we need to sort of backtrack, because when we study a different gauge fixing, so we study the Cauchy fixing gauge, which means we set ρ1 equal to RC over lambda. So then now the transformation between R and sigma with the new radial coordinate looks like this. What we have is that something quite surprising. Why? Because first of all, this transformation, what it does is to still map RH to sigma equal to 1. But then the Cauchy horizon, the RC point, is now mapped at infinity. So we're pushing the Cauchy horizon to infinity. And now the surface corresponding to R equal to 0 is mapping to a point, which, if you compute it, is a point that lies outside this domain. And this is a relevant detail that will be useful later. And why is this? Because now if you introduce this coordinate with this gauge fixing, the radial Teukolsky equation looks like this. This is a type of equation that I didn't show you before. This is called the alternative general form, whereby now the singular point, the regular singular point can be any point, doesn't need to be infinity. And in fact, here are labeled as sigma 2. Sigma I are the irregular singular point of the equation that now correspond to the point corresponding to the horizon and the point corresponding to the Cauchy horizon, which now is located at infinity. So what we have is an equation with two regular singular points corresponding to the position of the horizon and the Cauchy horizon, and one irregular singular point, which is now located at sigma infinity, which is actually 0. Why then we have two regular singular points? Because the point that was the new regular singular point in the radial fixing gauge in this context is outside the domain of sigma. So it's a negative point outside the domain. So we are somehow getting rid of the additional singular point that can be usually introduced by passing to hyperboloidal coordinates. So how can we then make sure that this is then really a confluent Heun equation? What we did is to then look at the traditional constraints that a point at infinity needs to satisfy to be an ordinary point of the equation. Why is that? Because sigma c is at infinity, so the equation will not have the sigma I corresponding to that point. So the coefficient at infinity will look like they're missing. So it will seem like the point at infinity is an ordinary point of the equation. So to check that is not the case, one needs to satisfy a certain constraint that are supposed to hold for this type of equation. If you check the constraints, these constraints are not satisfied. So infinity is really a genuine singular point of the equation. Now one needs to look at what type of singular point do you have. And in order to do this, you can pass to a new variable z, in which now the point that was at infinity is its final location. And if you do the analysis, you discover that there is a regular singular point of the equation. And in particular, that when we pass to z, we obtain an alternate, another form of the canonical confluent of an equation with two regular singular points corresponding to z, c, and zh, so the position of the Cauchy horizon and the event horizon, an irregular singular point corresponding to infinity. So we can conclude, and this is due to some questions that were raised when Rodrigo and I had a conversation with Lionel London. There was concern about this specific case, that we were wrong in our previous conclusion, that you can have an hyperboloidal foliation whereby you can recast the radial Teukolsky equation as a confluent Heun equation. So thanks, Lion. Now, we can also in this case perform the analysis by looking at the corresponding homotopic transformation. In this case, if you look at the homotopic transformation, they will deform the solution to the Boyer-Lindquist to the solution to the radial Teukolsky equation written in this coordinate within this gauge. You discover that now we have three exponent, mu c, mu h, and nu, that again directly relate to the plus configuration for Heun, and then in agreement with a next homotopic transformation only for an Heun configuration, the coefficient, the exponent corresponding to infinity is now missing. So this seems to support the idea that the radial Teukolsky equation written in terms of this coordinate is really a confluent Heun equation. So if you look, so if one wants to see what this foliation looks like, so we have that in the radiative region, the hyperboloidal foliation has the same property as the radial fixing gauge, but as we cross the event horizon and we move towards the Cauchy horizon, since this is now located in an infinite position for sigma corresponding to infinity, so at infinity, all these slices eventually will never cross and eventually accumulate at this point. The other interesting feature of the Cauchy fixing is that somehow this reproduced the same answers introduced by Lever in 1985 that allows the space-time interpretation of this approach as a frequency domain representation of the Teukolsky equation in the Cauchy fixing gauge. So then what we did is to then compare the two cases. So I have the radial fixing gauge, the Cauchy fixing gauge, and then what we did is essentially look deeply at the height function. So I called HRF the height function in the radial fixing gauge, HCF the one in the Cauchy fixing gauge, and then you can compare term by term. So what happens is the term that will determine how the solution behaves around the horizon has the same coefficient. But somehow, if you change the coefficient around the Cauchy horizon, what you do is to then cancel the term that will eventually, be related to this R here, that eventually will give rise to this additional singular point that are equal to 0 for the in the radial equation when you pass to hyperboloidal coordinates. So somehow your choice of height function can then control the fact that you can eventually have the desired number of singular points and the desired confluent Heun equation out of your choice of hyperboloidal coordinate. Okay. So in conclusion, what we did is to review the use of Heun function in solving the radial Teukolsky equation, and we show that a space-time level transformation really represents the effect of passing to a coordinate set and using an S-homotopic transformation. We introduced the concept of Heun slices. Heun slices is one of the correspond to the choice of coordinate transformation related to the choice of mu, nu, and then demonstrated that a canonical confluent equation can arise from specific space-time foliation with configuration that we label as triplets. Then highlight the importance of the slicing configuration for the asymptotic behavior of the radial perturbation, and they are related to the characteristic exponent. They relate the characteristic exponent to the property of the solution around the infinity, I naught, and time infinity. And in the end, what we did is to explore hyperboloidal coordinate. Note there's some height function choices, like the Cauchy fixing, that are still compatible with the minimal gauge, can lead to a radial Teukolsky equation written as a confluent Heun equation. And that's it. Thank you.